Hey everyone. This is a new episode of the Machine Learning at Lunch here at Gemma AI, and today we have Eduardo, a machine learning engineer, which will be explaining vision transformers, so what they are and what they are capable of, and their application. So, without further ado, Eduardo, please.
Yeah, good afternoon, everyone, and thanks, Giacomo, for the introduction. So today, the vision transformers are considered a new horizon in NLP, natural language processing, but also in computer vision. And since we are building an architecture exploiting this technology, we thought that can be useful to have an overview on that. So to understand vision transformers, we need to start from transformers architecture that was introduced in the 2017 in the paper Attention is all you need. And this is one of the most cited paper in this field. So at the core of this model lies an unique components that is the self-attention mechanism. This mechanism gives the possibility to focus and prioritize on different parts of the input sequence. In this way, is given more importance to relevant parts, and at the same time, understanding the context of a word. And this is possible because this model can understand and learn long-term dependencies inside the sentence. So unlike traditional models that process data sequentially, transformers understand the context in parallel. So this type of learning lead to improve efficiency and also increasing the accuracy of the overall methods. As we know today, the large language models are like the base of the attention mechanism, and the capabilities of these models are stunning. So building on the success of transformers in the realm of natural language processing, researchers thought to extend the replication into another domain, the one of the images. And here, the vision transformers, or for short, VITs, come into picture. So vision transformers take the essence of transformer architecture and apply to image analysis. So instead of looking the image like a static 2D object, vision transformer approach the image like a sequence of pixels, similar to how you'd see a sentence as a sequence of words or a sequence of tokens in detail. So the beauty of this approach is, as I said before, that allows VITs to understand long-range dependencies within the image. This is similar to how can understand the meaning of a sentence by looking at the different interaction of its words. So we are talking about how do you do vision transformers work. So firstly, an image is divided into small pitches, and these patches are small pieces of the image. You can see from the image that is that came from the original paper that introduced the vision transformers. So these patches are linearly embedded. So that means that in the context of VIT is a transformation in a numerical vector that can then be processed by the model. In fact, we know that the model don't see images, but see like numerical vector. Then they add an important feature or information. It is the position of the patches inside the image. So the transformer encoder then process this sequence of patch and position embeddings, and in this way generates a comprehensive image representation. I want to add that in our case of audio classification, the positional embeddings are very important because we can add information about frequency, both frequency, but also time inside the patches. And this we can obtain improvements in the developing of our models using this technique.
So you're saying that essentially here, if you were just talking about a random like an image from real life, like this one, yeah, the numbers might just mean, you know, top left angle, whatever, center, and in the case of a spectrogram, actually the top left angle, that would be high frequency and first chunk of, you know, wave file or whatever. So it actually carries some additional information. That's what we are trying to achieve, right?
Yeah, you're right.
Okay, that's cool. Okay.
So another question is how well vision transformers perform. So they match and or also exceed the performances of traditional convolutional neural network in many benchmark datasets, including one of the most famous, that is ImageNet. So regarding the field of audio classification, that as we said before, are images. The vision transformers are the state of the art in almost every benchmark dataset of today. Obviously, there are different type of vision transformers. There isn't one that is better for everyone, but in every benchmark dataset, as I said, is the state of the art is based on vision transformers. However, it's important to challenge to say what are the challenges of this approach. The first is that you require large-scale datasets. In fact, transformers need a very big chunks of data to be trained, and also significant computational resources to achieve these results. So in the future of vision transformers, there are a lot of promises. We are already seeing trends like hybrid models that are emerging nowadays. This architecture trying to combining the strengths of CNNs and the vision transformers to leverage the best of both models. So these architectures have found a lot of application in the field of computer vision, like for example, object detection, image classification, or segmentation, and a lot of other tasks that before was done using CNN. However, this is also a relatively new technology, and there are a lot of exploration and improvement that will be done in future. And we hope and believe that is a near one. So with that, I'd like to thank you all for your attention and look forward to your questions.
I just have one, and that would be how are these guys using Vision Transformer in combination with the CNN? Are like, I don't know, two different nets, and then you combine the results at the end, or is uh, or not even that, or something more specific? Just curious if you know the answer.
I think that like the simplest approach is using an ensemble. So take the outputs of different models and then make an ensemble. Um, so like based on the performances of different models, we will assign weights to the output and the prediction of each model, and then combine this prediction to give the final answer.
Yeah.
This is the simplest approach that I thought 1 minute about it.
Okay, Eduardo, I also have a curiosity. In the paper that you have read, the author studied also how the dimension of these patches influence, for example, the results and the outcome of this visual transformer.
Yeah. In fact,
Or
the
what do you think?
paper, yeah, the paper highlights also in the title 16 for 16 pixels as dimensions of the patches. And this is important because all these patches, each one is then like embedded in a numerical vector. So the dimension of this vector is given by the dimension of of the the images, not the images but the patches. So if you take a patch that is too small, the vector will be too short, and the model can't learn efficiently. Otherwise, if you take a patch that is very big, the vector will be too long, and there will be some problems during the training of the model, because maybe the dimension of the network will be too high to be trained.
Okay, thanks. Clear.
Okay, if there are no further questions, well, let's thank Eduardo for the nice introduction to the Vision Transformers, and I will see you guys in the next episode.